Hi everyone, here's Ned Koch for MIS5390. This is the second video of week 6 of the course. By 1 p.m. on Friday, tomorrow, you must post a commentary on what you've done during this week. Today I want to mention a few papers that are linked on warppls.com, that website. You can get to that website by clicking here, warppls.com. One of the articles that I wanted to highlight is this one, using logistic regression in PLS-SEM. It talks about dichotomous endogenous variables, but it is the same principle. It discusses the same principle and provides a tutorial on the same approach that I used in the mobile phone study by the team that studied mobile phones policies. In that particular project, I actually converted one variable into a logistic regression variable because the R-squared there was too low. And this tutorial talks about another situation where using logistic regression makes sense, and that's with dichotomous endogenous variables. The same situation as the one in the project. The dependent variable or the endogenous variable does not have enough variation in it for the R-squared to be higher of an acceptable value. So you convert the variable into a probability. The other article I wanted to mention is this one, and this is related to this statistical significance and effect size tests in SEM, structural equation modeling. And this is an article that talks about something that I mentioned in connection with the mobile phone project as well, which is that when the sample size is large, you have to be careful about using statistical significance tests like p-values, confidence intervals. We use p-values in our analysis here. I talked about p-values, but the software WarpPLS reports confidence intervals as well. The test is about the same. And I mentioned there that with large samples, a lot of things, very tiny effects become significant. So you have to be careful with that with large sample sizes and use effect sizes in your assessments of the results. And if the effect sizes are too small, then you should reject the effects as essentially being too small to be credible. Another article that I wanted to mention is this one, Theory-Driven Multigroup Analysis via Latent Growth in PLS-SEM. This article talks about something similar to what I used in the English language project, and that was a categorical to numeric conversion, which I did there to include the variable in the model. So this is the project here. So I actually used categorical to numeric conversion using the categorical variable models B, A, and C, to generate a set of scores that refer to those categories. And those are 3 sets of values. So this article here talks about something similar, but in this article I actually used the new converted variable into for a latent growth analysis, which is more like a moderating effects analysis. So this is an interesting article as well, if you are interested. So these articles that I'm presenting today, they are not required reading, but if you're interested in taking a look at them, it would add to your knowledge about data and model-driven data analytics. And one final comment that I wanted to make is on this project. So I converted the categorical variable on the spreadsheet model into a numeric variable. And then I showed you how that looks on a graph. So I'll go to that graph again. And it is this graph here connecting model to retention. And here I use the relationship graphs with data points and legends. And because that link connects two variables, but there is only one variable pointing at the other, not multiple, using the multivariate or bivariate doesn't make any difference. So I'll use the bivariate and unstandardized scales. And then I will go to settings and I'll choose models the data labels to be shown as legends. So here I have, so model A is Massachusetts, model C is New York and New Jersey, and model B is Texas. Now the scales are standardized, but the important one is this one, because this new numeric variable was created in a scale that is originally standardized. So even if I choose to show unstandardized scales, this one will be on a standardized scale. And on standardized scales, the difference between points like this one and these two, they can be interpreted in a particular way. So a 1 standard deviation difference is a large difference. A 2 standard deviation difference is a very large difference. So as you can see, the score for Texas is 1.5 and is standardized. The scores for Massachusetts and New York and New Jersey are actually below 0. 0 is around here, so they're both negative. So this essentially means that the difference between Texas and the other two is actually more than 1.5 standard deviations. And this means that it's between large and very large. Another way of saying this is that Texas is far different from the other two models. So, which is something interesting that you may or may not want to highlight in the model. So that's what I had for today. Thank you for watching.